Hey tens! Today we're going to learn about the properties of exponents. We know that multiplication implies repeated addition, and just like multiplication, exponents mean repeated multiplication. But how do we work with them? And how do we simplify expressions containing exponents? That's what we'll be exploring today in this video. Some terms to know. An exponent is a number that implies how many times another number, or base, must be multiplied by itself. So I have this equation here. 2 to the power of 3 is equal to 8. And this is a true statement. But what are the parts of this number, 2 to the power of 3? What is the base and what is the exponent? And how do exponents work? Well, to find that out, we can turn to multiplication, as it is pretty similar to exponents. So I'm just going to write a similar equation. 2 times 4 is equal to 8. Now this is multiplication, and multiplication is repeated addition. So looking at this, if we want to write this in repeated addition, there are two ways we can interpret this equation. The first way we can interpret it is that 2 is being added to itself 4 times. So this would equal 2 plus 2 plus 2 plus 2. Another way we can write this is 4 is being added to itself 2 times. So 4 plus 4. And if you add these up, you'll find that both of them equal 8. But with exponents, we don't have this commutative property. 2 to the power of 3 is not equal to 3 to the power of 2, or 3 squared. Another common misconception, or rather a silly mistake, is that in a hurry, you might think of 2 to the power of 3 as 2 times 3, but that is not true. 2 to the power of 3 is not equal to 2 times 3, and you can see here that 2 times 3 is not equal to 8, it's equal to 6. So, given all this, how does 2 to the power of 3 work? 2 is our base. It is the number that must be multiplied by itself, however many times the exponent implies. 3 is our exponent. It tells us how many times 2, or the base here, must be multiplied by itself. So, given this, we can say that 2 must be multiplied by itself 3 times. So this is equal to 2 times 2 times 2, because repeated multiplication. But what does this mean? Let's go a step further and write this as repeated addition, because it seems very obviously that these two are equivalent. But how? 2 times 2 implies that you are adding 2 to itself twice. So this is equal to 2 plus 2. And then you multiply that by 2. And that seems a little confusing. To make it less confusing, we can evaluate this 2 plus 2 and make it 4. And then multiply that by 2. So we would get 8, right? And we can see here that 2 times 4 is equal to 8. And that's the same thing. 4 times 2 is also equal to 8. So we would have this. You can also think of it as you're adding 2 more 2's because there are already 2 2's here. And that's a lot of 2 2's. Yikes. But enough with the jokes. How would we solve an equation like this, where the exponent is equal to 0? What does that evaluate to? Well, there is a property that explains what value this will equal, and several more properties that will come of use when simplifying expressions with exponents in it. So let's move on to the next slide. The properties of exponents. There are several properties of exponents that you want to remember and make use of. The first one is the zero property, which we just saw in the last slide. The zero property states that any non-zero real number raised to the power of 0 is equal to 1. So what this means is that, like in the previous slide, 2 to the power of 0 is equal to 1. But so is 4 to the power of 0. And so is 10 to the power of 0. I mean, you can even say that this number, whatever it is, to the power of 0 is equal to 1. No matter how big the number is, it will always equal 1 if it's raised to the power of 0. Now, the only exception of this is 0, because it says non-zero. So what is 0 to the power of 0? Well, 0 to the power of 0 is undefined. Now, the reason for this is beyond the scope of this video, but if you're interested in figuring out why, I've put a video in the enrichment resources which you can look at that explains why 0 to the power of 0 is undefined. The next property that we're going to see is a negative exponent. A real number raised to a negative exponent is the reciprocal of that number raised to the positive exponent. So an example of this would be 2 to the power of negative 1. Now, we can see that we have a negative exponent here. This means that 2 to the power of negative 1 is going to equal the reciprocal, so 1 over the number raised to the positive exponent, so 1 over 2 to the power of 1. And this introduces another property which doesn't exactly have a name, but it is also helpful to remember, that any number raised to the power of 1, yes, even 0 raised to the power of 1, is going to equal that number. So the base is 2, yes? If we raise it to the power of 1, we're going to get our base. This is because, well, if you think about it, if you multiply 2 one time, you don't really have anything to multiply it by except 1, so you're just going to get 2, or whatever your base is. So this will simplify to 1/2. Another example is 4 to the power of negative 2. So this will equal the reciprocal 1 over this number raised to the positive exponent, so without the negative. So this is going to equal 1 over 4 squared. And 4 squared is equal to 4 times 4, because we're multiplying 4 by itself twice. And so this will simplify to 1/16. And so on like this. Now, another thing you want to remember when you have something like this property is that the opposite also holds true. So if you have something like 2 squared, this is going to be the reciprocal of the negative exponent. So it's going to be equal to 1 over 2 to the negative 2, okay? The next property is the product of powers. When two exponents with the same base are multiplied, the exponents are added. So what this means is that if I have two exponents, say 4 to the power of 2 times another exponent, 4 to the power of 6, notice that they have the same base. If they don't have the same base, you can't use this property. And because they have the same base, we can add the two exponents. So this will equal 4 to the power of 2 plus 6, that whole exponent, which is equal to 4 to the power of 8. Now, why does this work? Well, let's take our exponents and write them as repeated multiplication. So 4 squared can be written as 4 times 4, and 4 to the power of 6 can be written as 4 times 4 times 4 times 4 times 4 times 4, right? And we're multiplying these together. So we're multiplying this by this. But of course, all of these are multiplication. We can just remove the parentheses. The parentheses don't really matter in this. So this is basically saying we're multiplying 8 4s together then, which is equal to 4 to the power of 8. So that is why this property works. We also have the quotient of powers. This is when two exponents with the same base are divided. When this is so, the exponents are subtracted. So it's like the inverse of this. So let's take the same example here and divide them. 4 to the power of 2 divided by 4 to the power of 6 is equal to 4 to the power of 2 minus 6. Yes, we subtract it, which is equal to 4 to the power of negative 4. Now, using the negative exponent property, we can simplify this to 1 over 4 to the power of 4, which is equal to 1 over 256. Now, why does this work? If we take these and use repeated multiplication again, we would get 4 times 4 for 4 squared divided by 4 times 4 times 4 times 4 times 4 times 4, 4 to the power of 6. Now we can cancel out any of the 4's in the numerator that are also in the denominator. So these two 4's cancel out and these two 4's cancel out, leaving us with 1 on the numerator and 4 times 4 times 4 times 4 on the denominator. Now this is equal to 4 to the power of 4. So we get 1 over 4 to the power of 4, which is also equal to 4 to the power of negative 4, which is equal to 1 over 256. Alright, the next property is power to a power. When an exponent is raised to another power, the two exponents are multiplied. An example would be that 2 squared raised to the 7th power is going to equal 2 to the power of 2 times 7, which is equal to 2 to the power of 14. Now, why does this work? We can use repeated multiplication again to prove this property. So if we write 2 squared as repeated multiplication, that would be 2 times 2, right? And we raise it to the power of 7. Now let's evaluate 2 times 2. 2 times 2 is equal to 4. So this is the same thing as 4 to the power of 7. And 4 to the power of 7 is equal to 4 times 4 times 4. Yeah, you get my meaning. Is that 7 4s? Yep. Alright, so 4 to the power of 7 is equal to this thing. But 2 times 2 is equal to 4. So for every 4 we have here, we have 2 2's that are multiplied together. So this would equal 2 times 2 times 2 times 2. Yeah. 2 2's for every 4 here. Now if you count up these 2's, you're going to get 14 2's being multiplied together. And that is equal to 2 to the 14th, which is why this property works. Next property is the power of a product. Now, The name sounds similar to product of powers, but this property is different. It states, when the product of two numbers is raised to an exponent, it is equal to the product of the factors raised to that exponent. Now this sounds confusing in words, so let's use numbers to make more sense of it. So what this means is that if we have two numbers being multiplied together, it's like 2 times 5. Yes, I like using 2 a lot, okay? Don't blame me. And we raise this whole thing to an exponent, say 3. We can write this as 2 to the power of 3 times 5 to the power of 3. But why does this work? Again, we can use repeated multiplication to prove this property. So, let's take this and evaluate 2 times 5. 2 times 5 is 10. So, 2 times 5, in parentheses, to the power of 3 is equal to 10 to the power of 3. 10 to the power of 3 is equal to 10 times 10 times 10. Yes? But within each 10, like here, there is a 2 and a 5 being multiplied together. So this is also equal to 2 times 5 times 2 times 5 times 2 times 5. Now notice here that we have 3 2's multiplied together and 3 5's multiplied together. So since we can use the commutative property here, this will be 2 times 2 times 2 times 5 times 5 times 5, which is 2 to the power of 3 times 5 to the power of 3, because you have 3 2's being multiplied together and 3 5's being multiplied together, which is why this works. We also have the power of a quotient, which is once again the inverse of the previous property. When the quotient of two numbers is raised to an exponent, it is equal to the quotient of the factors raised to that exponent. So, a prominent example is fractions. When you multiply fractions, you multiply the numerators together, and then you multiply the denominators together to get the numerator and denominator of your product, right? So, if we have, say, 1 divided by 7, which is also equal to 1/7, because fractions are division, and say this is cubed, this is equal to 1 cubed over 7 cubed. And why this works is because if you did 1/7 cubed, you would do something like this. 1/7 times 1/7 times 1/7. And when you're multiplying fractions together, again, you are multiplying the numerators together to get the numerator of your product, and then you're multiplying the denominators together to get the denominator of your product. So 1 times 1 times 1 is equal to 1, and 7 times 7 times 7 is equal to 343. But since we have 3 1's being multiplied together here, we can write that as 1 cubed. And since we have 3 7's being multiplied together, we can write that as 7 cubed, which is equal to this. Alright, now that we know the properties of exponents, how can we use them to simplify an expression with exponents? Well, the answer is obvious. We use the properties. And we're going to be using variables here. Okay, in algebra, when we have an expression with exponents, we use variables that are raised to exponents. But when we're simplifying expressions where a variable is raised to an exponent, we always assume that the variable is not going to be a value such that the exponent is going to be undefined or the whole expression is going to be undefined. So we use the properties, right? Some examples of using the properties are, if a variable is raised to 0, cross it out because it's equal to 1. If a variable is raised to a negative exponent on the numerator, put it on the denominator, and vice versa. So if a variable is raised to a negative exponent on the denominator, put it on the numerator. Why is this so? As I explained a few slides back, if we have something like x squared over 1, because, well, that's what x squared is, if we take the reciprocal of this, it would equal 1 over x squared. And 1 over x squared is equal to x to the power of negative 2. But if we take the reciprocal of x to the negative 2, we get 1 over x to the negative 2, which is equal to x squared. Because, let's take this with numbers, if you have 4 and you want to find the reciprocal of that, this would be 4 over 1, and you'd flip the numerator and denominator, you'd get 1/4, but the reciprocal of 1/4, you'd flip the numerator and denominator here, and you'd get 4, or 4 over 1. So it's the same thing here. If a variable raised to an exponent is being multiplied or divided by another exponent with the same base, you have to remember that you can only use the product of powers and quotient of powers properties if the exponents have the same base. You can add or subtract the exponents respectively. So if you have exponents being multiplied, then add the exponents. If they're being divided, subtract the exponents. If the whole expression or some part of the expression is raised to the power, distribute that power. This is the first thing you want to do. You want to use the power of a power property first before you use any other properties. And if you have two constants being divided, simplify that. It's like a fraction that you need to simplify. Two things to remember. Exponents mean repeated multiplication, so if you have addition and subtraction, you can't use any of the properties. And no negative exponents are allowed in the final answer. So, knowing all this, let's try some examples. This one will be with no variables. And before I show you how to do these, I encourage you to pause the video and try them out on your own. Alright, I'm assuming that you've tried them out, so let's do the first one. 2 cubed divided by 5 cubed. Now, this is using a power of a quotient property. So, 2 cubed divided by 5 cubed can be written as 2 divided by 5, or 2/5 cubed. But this is unnecessary. We can already evaluate these. So 2 cubed is equal to 2 times 2 times 2, and 5 cubed is equal to 5 times 5 times 5. So we can evaluate those, and we get 2 times 2 times 2, which is equal to 8, over 5 times 5 times 5, which is equal to 125. And this can't be simplified, so we have 8 over 125 as our answer. Let's do the second one. 7 to the power of negative 1 plus 3 squared. Now, using the negative exponent property, we can simplify this to 1/7. Then we add 3 squared, and 3 squared is equal to 9. Now, this is a trick question in that it's using addition. They're adding the two exponents together. If it were multiplication, you still wouldn't be able to use the product of a power or quotient of a power properties because they have different bases. So we have this 1/7 plus 9, and we get 9 and 1/7 as our final answer. Now, you can make this an improper fraction if you want, but I prefer not to because it's an extra step and you can make mistakes with extra steps. Alright, now that this is done, let's simplify expressions with variables. Now, these are significantly more complex than the ones shown in the previous slide, but I still encourage you to pause the video and try them out on your own. Alright, I'm thinking that you've tried them out, so let's do the first one. 2x squared in parentheses squared divided by 8x to the power of 6. So again, as I told you a few slides back, you want to use the power of a power property first. And we can see that we have that property here. So we need to distribute this power. Now, if you're thinking that I'm just going to distribute the 2 here to x squared, you would be incorrect, because since the 2 is also in the parentheses, you need to distribute the power to the 2 as well. So 2 is the same thing as 2 to the power of 1, so there is an invisible 1 there. And 2 to the power of 1 squared, 1 times 2 is equal to 2, so you would get 2 squared. X squared to the power of 2 is 2 times 2 is equal to 4, and we would get x to the power of 4. This is all over 8x to the power of 6. Now we can simplify 2 squared to 4, and so we would get 4x to the 4th over 8x to the 6th. Now, when I see two constants that have a GCF greater than 1, I will just simplify those because, well, it's part of the simplification process. So we can simplify this to 1x to the 4th over 2x to the 6th. Okay? Now, if you're thinking you're done here, you would be incorrect, because x to the 4th can be divided by x to the 6th. They have the same base. So we can write this as x to the power of 4 minus 6, which is x to the negative 2. So this is equal to x to the power of negative 2 over 2. And now we're still not done, because we don't want any negative exponents in our answer. So we need to move this to the denominator to make that exponent positive. So this would equal 1, which is all that's left up here. It's not 0, over 2x squared. And now this is our final answer, with positive exponents only. Alright, let's do the second one. 5x cubed y to the 5th z squared over 6x to the 6th z to the negative 4th, all to the power of 4. Again, when we have a power to a power, we want to distribute that power to every term here. So we distribute the 4 to even the constants again, and we get 5 to the 1st is equal to 5. 1 times 4 is equal to 4, so we have 5 to the 4th times x cubed. 3 times 4 is equal to 12, so x to the 12th times y to the 5th. 5 times 4 is equal to 20, so y to the 20th times z squared. 2 times 4 is equal to 8, so this is z to the 8th. And we get that over, again, since all of this is in parentheses, we have to distribute it to all the terms in this parentheses. So we get 6. 6 to the 1st is 6. 1 times 4 is equal to 4, so we get 6 to the 4th times x to the 6th. 6 times 4 is equal to 24, so x to the 24th. Z to the negative 4th. Negative 4 times 4. Yeah, don't worry about the negative exponent just yet. We need to distribute the power first. Negative 4 times 4 is equal to negative 16. So we get z to the power of negative 16. And don't forget that negative. The negative is important. Alright, so we have that. Now let's simplify these constants that have been raised to the exponent. 5 to the 4th is equal to 625. And let's just add everything in after that. So x to the 12th, y to the 20th, z to the 8th, over 6 to the 4th is equal to 1296, x to the 24th, z to the negative 16th. Now, even though these two are huge numbers and it looks like they can be simplified, they cannot be simplified. And a way to figure this out is by looking at the original one before they were raised to the exponent. And if it is in simplified form, when you raise it to the exponent, it's probably going to be in simplified form already. So, 625x to the 12th, y to the 20th, z to the 8th, over 1296 x to the 24th, z to the negative 16th is what we have right now. So, instead of moving this to the top just yet, let's divide all of these first. So, x to the 12th divided by x to the 24th, 12 minus 24 is equal to negative 12, so we have 625 x to the negative 12th. Now, if you're asking me why I put this on the numerator, it's because when you divide, you're going to move it to the numerator. If it's going to end up as a negative exponent, you'll move it to the denominator anyway. But the default is moving the exponent up to the numerator. Since there is no y that we can divide by on the denominator, we will leave the y alone. So we have it as y to the 20th. And since we have z on the denominator and the numerator, we can divide those. Z to the 8th divided by z to the negative 16th. We subtract the exponents. 8 minus negative 16. Subtracting a negative is equal to adding a positive. So 8 plus 16 is equal to 24. And we have z to the 24th over 1296. The x and the z we've already removed by dividing them, so we have 1296 on the denominator. Now, we have our simplified version, except we have negative exponents in here. So we need to move the negative exponents to the denominator. X to the negative 12th is a negative exponent, so we move that to the denominator, and we get 625 y to the 20th, z to the 24th, over 1296 x to the 12th as our final answer. Alright, that's the end of this video, so thanks for watching. If you liked this video or this helped you, click that like button. If this didn't help you, click that dislike button. I greatly appreciate feedback. If you want more updates on new videos, click that subscribe button and turn on notifications. If you have any questions related to this topic, please put those in the comments below. And remember, the comments section is equivalent to a class discussion, so if you have any answers to any of the questions, you may answer them. If you have any suggestions as to how I can improve my future videos, or even what I should do next, please put those in the comments below as well. If I like your suggestion, I'll be sure to include that in the next video and give you a shout out. See you in the next one!